we'll try to cover today the last two attention mechanisms which are presented in this book. And let me share my screen. As this book says, the logic of these mechanisms are built one on top of the other, which means that in order to understand causal attention, which is the third attention mechanism, I will need to take one step back to go to the previous attention mechanism, which was presented in the book. Let me tell you if you can see my screen. Can you see my screen?
Yes, we can.
Okay. Okay. So I need to go in presentation mode. Yeah, I hope you see my screen. Okay, so just a recap from the previous discussion, we have this simplified technique or mechanism, the self-attention mechanism, and the idea here that we need to build an enriched meaning or representation for each word in a sentence using this context vector approach. The second mechanism is self-attention with trainable weights. And here in this mechanism, these weights, which we'll see that basically there are three matrices, will be trained and will allow the model to better understand how each word relates to the other words in a sentence. So in this chapter, we will go through the we'll go only to the fast forward mechanism. The backpropagation will be presented in, I think it's chapter 5. But the point is that these trainable weights are trained during the training phase in self-attention mechanism. The first mechanism which will be discussed today is causal attention technique. Here, the idea is to implement within the large language model a human-like approach. And a human-like approach is that whenever we talk, we focus on the last and the latest word somebody says. And then if somebody wants to predict what will be the next word, the prediction takes place knowing all the words up to that moment. And last mechanism is multi-head attention, which is basically a extension of the causal attention, and it is basically a kind of creating multiple variations of this causal attention, which will be defined as being a head, and basically multiple heads will be simultaneously careful to various aspects of the input in order to extract as much understanding from the input and to make, of course, the prediction of the next token better. Okay. So this is the short recap from the trainable weights in order to have a meaningful understanding of the causal attention. So just short, because we will discuss extensively with these three concepts: query, value, and key. So again, we had a sentence, which is an input from the large language model, and within the sentence, every word will play three roles at any given moment. It will play the role of the query, will play the role of the key, and the role of the value. And these three functionalities are implemented using these concepts, query value and key, which are implemented within matrices, within weight matrices, WQ, WK, and WV. The idea again was that different tasks have different approaches to relate to the input. For example, summarization and is one use case which will require a different skill set than for the large language model than, let's say, standard text generation. So for summarization, for example, the model should have the capability to identify the keywords in a sentence and to make a short summary out of something, while the text generation use case or translation use case, I should say, requires a different approach from the large language model. It must be careful and pay attention to everything, to every single word within the sentence, because a word can change the complete meaning of a sentence. So that's why for each use case, the researchers created different set of weight matrices, or different set of matrices which contain these weights, in order to solve different problems. And of course, during the training process, these weights have, let's say, different dynamics across time. Again, considering the same input for the large language model, which in this example is this sentence: your journey starts with one step. Yeah, with one single input, we can apply to one single input multiple use cases, like I said, translations or summary. That's why these matrices are so important. Okay. Okay. Now I'll need to run the code. Let me see how can I share my second screen now. So the first step is we take the input sentence, which is your journey starts with one step. We have here 6 words. We convert them in 6 tokens, and each token then is converted into a vector embedding. In our case, it's a 3-dimensional vector embedding. Let me see how. Yeah, I see. I need to move my window. So this is the code from the book. Can I see my collab?
Yeah, your collab.
Okay. So as I said, the way this chapter is, let's say, designed is to present these mechanisms one on top of the others. So in order to have a good understanding of causal attention, we need to run through the previous 2 mechanisms, most importantly the trainable weights mechanism. So here we import or here we define the tensor, which represents the 3-dimensional embedding for our input, our sentence input, which can start with one step. This is just an example from the previous mechanism. I'll try to focus only on the relevant parts of the code. This was a simple causal attention. Okay, so now we are in the second part of the chapter, which is relevant to causal attention mechanism. So now we take as an input the second element, which is called x_2, and we define, we need basically to project this input into a matrix, which has a 2-dimension output and 3 dimension for the input. The author says that Sebastian says that normally these dimensions are the same for the input embedding and output embedding. He just want to make the case to see how an input can be projected into a 2-dimensional embedding matrix. So now we have these 3 matrices for this example: W query, W key, and W value. These are initialized with some random values using these two dimensions, the input, which is 3, and the output, which is 2. So we have a 3-dimensional embedding vector for the input, and we'll have a 2-dimensional embedding for the output. If you remember from the previous discussion we had, we need to compute with values by multiplying the input with the W value matrix. Actually, I think one more thing here about this causal mechanism. Why it's important? I think I skipped this part. This causal mechanism is important because just in real life, we want a large language model to pay attention only to the words or to the tokens up to the current moment. So, because I want for the large language model to look at a word, let's say journey in this example, to look at the word, and I want to know how much attention the large language model should pay to the other words before the word journey. So, because I want to compute the context vector for this word, taking into account 2 things. I want to take into account the semantic meaning for the word journey, but also I want to encode in this context vector. I want to encode also the meaning about how journey relates to the other words in this sentence. So again, we want to make this attention we want to make the model to pay attention up to the current token, not to the future tokens. So let's continue here. I want to get to the point where I need to multiply the inputs with the query key and value weight matrices. So these are the steps. Okay, so now I'm to the causal attention section of the book. So again, I put again the inputs, which are the embedding representation of the inputs actually. I'm using the query and key weight matrices, which were computed by self-attention version 2 class. And I'm getting here the weights by applying softmax on so the attention score is let me see here. Okay, so we need to also to compute the attention score like we did in the previous two mechanisms, which is the multiplication between the query matrix and key transposed matrix. And within this matrix, an element ij will represent the attention score between the ice query with regards to the j key. And basically, what I want to provide a similarity score between all the possible pairs, query and key, because every word in a sentence becomes at one moment a query, and then this query will let's say will query all the other inputs in that sentence, which will act as a key. And basically, I want to see what is how close, how similar is this word which acts as a query with regards to all the other words within the sentence, which are now called keys. So I compute this dot products and in order to find how similar are these words within this context. And the goal is to, if we have a sentence with 6 words, like is the case, the journey starts with the first step, I want to compute the attention scores for all the input elements, for all the words or tokens, in regards to all the others, which will become a matrix 6 times 6 basically, which is okay. So let me switch back to the code now. Yeah, so this is the attention score matrix. Yeah, so let's take first line here. Yeah, first line represents the attention of the query 1, which is the word the, to all the other keys in the sentence. Line 2, which corresponds to the token which represents the word journey, represents the attention of this query, which is called journey, in regards to all the other keys in the sentence, in the input sentence. So let's try to go deeper here. So first number, which is 0, 20, 41. So it represents, so when I'm looking at the word journey, when the large language model looks at the word journey, then they say, okay, let's see how much attention should I pay to the first input, which is the, and he decides that it's 0, 2. Then the large language model looks again and say, okay, when I'm looking to the query step, how much attention should I pay to this word step, and it computes this number 0, 14. So this is how this attention score matrix should be interpreted, or yeah. Okay, so as you can see,
Yeah,
and the
just
next
a question.
Step, if any questions, yeah.
In that example, we haven't masked, right? That's where you're heading to. Or did
yeah, we didn't.
Okay. Cool.
Okay, so
okay, there it is.
okay, okay. So if you I need to take one step back, because I want to give you an insight of the problem, because we are going to have, let's say, some issue pretty soon. So we've seen in the way in which we computing the softmax, when we apply the softmax function, which slide was? Yeah, so here we need to make a normalization to make all the elements on one row to sum up to 1 in order to read them as probabilities. Yeah, and we applied we use this square root of the key dimension, which was defined earlier, and we applied the softmax function. I need to show how the softmax function looks like. So this is the definition of the formula for this function. I know looks a little bit scary, but it's important. So is e to the power of zi divided by the sum of the elements on a particular row. Yeah, which is a softmax function. So now in our case here, okay, so we need to keep that in mind at the moment. Yeah, this what is the definition of softmax function? I will come back to this one. Okay, so the idea is okay. Let me see how can I better describe the need for such approach to make all the elements above the diagonal 0. So what happens here? So when a large language model is looking to visit to an attention score matrix, a particular query, let's say in this example, journey, which is 0, 16, 59, basically it looks at the entire row at once, which means that when large language model computes this attention score matrix, I want the causal attention mechanism, or to factor in, to take into account only the tokens which occurred at or before that current state of the sequence. I don't want the attention mechanism to factor in all the attention scores which are already computed, because this is like it's like cheating for an exam from the large language model point of view. So when it's like large language model knows already the answers, because the job of the large language model is to predict the next token. So somehow the large language model should not be aware of the next token, because this is what his job, to minimize the difference between the predicted token and the real token. So this is the reason. This is the reason why we need to basically to make 0 all the attention scores which are above the diagonal. I think it's very important to grasp this concept, because it's key for this attention, for this causal attention mechanism. If you have any other ways of reading it, or
I have a question.
Go ahead.
Yeah, I have a question. I don't know if anyone knows the answer, or maybe we will see that in the future when we start training the model. But my question is, I'm not sure how this is necessary when we are doing inference. I mean, I understand that it's necessary for the training, because if I'm training it and I'm telling it the future, then kind of we are cheating, as you said. But if we're doing inference, I don't really understand why we need to also do that. We're not doing it just when it's in training. It's also going to be masked when we are doing inference, and maybe it makes sense. Maybe it's something like we also wanted to only think on the next token, so we don't want it to think on the next after the next or something like that. But just I'm making just a question out loud because it's one of the things that I didn't get yet. But well, that's one of the things that I haven't
Okay, you know how can I answer to your question? So let's imagine that we have a student, yeah, and we want a student to be able to be competent in one domain, and it is the job of the university or whatever, YouTube, to teach him the fundamentals. We want this guy to understand the fundamentals in order to be able to generalize for unseen problems in his job, yeah. Which means that we have two different aspects of the process. We have a training process where we want to teach a student to be a good employee, yeah, and to be a good expert in his area, and to be able to generalize based on his fundamentals, to be able to generalize and to solve future and unseen problems. And then we have the same student, which now is an employee in an organization, and we want to use this employee to perform his job as much as he can. So we have two different things here. Yeah. So we want to make sure that when we train the student, this guy is able to learn the fundamentals of his domain so good that he will be able to solve any variations within his area of expertise. I hope it makes sense. So these two things are, this is how I see them. I see them separately. Yeah? I see the training process where I want to make sure that this stuff is so smart and is not cheating. Because if it's cheating, what means cheating? Cheating means that in real life, cheating means that you don't learn well. Yeah, you didn't learn something good enough. This is cheating. Yeah, you learn already the answers, and which means that you didn't learn it correctly. Yeah, so which means that what you know is your expertise is just that set of questions for which you know the answers. Yeah, but you are not good in that field. You are not good in that field under any. You know, there is a discussion about IQ, by the way, by psychologists, and they say, okay, how can you improve the IQ? And they say, okay, if you learn if you take these IQ tests over and over, you are so good and so fast solving these IQ tests, and you probably will take a big score, but does not make you smarter, does not reflect your real IQ. You are just good at that particular IQ test. Yeah. I think this is the best metaphor I can find for this attention, because the people which develop this stuff had deep insights into how the human psychology works. And I see a lot of, I also study psychology once in a while, and I see a lot of similarities and things which are mapped one-to-one almost to this field, which apparently should have nothing to do with language or with data science for that matter. So yeah, so this is how I see it. You want to compute these attention score weights only with the data you have at the moment in the sentence, which is a sentence is chronologically speaking is it's something which happens across time. Yeah, so I want sure that predictions, yeah, this is my target. Yeah, I want the large language model predictions. I want these predictions to be done only using the context from prior tokens, which basically is mimicking the way in which language is naturally produced. Yeah. For example, let me try to find another example.
Just one question
Yeah,
to Carlos.
yeah.
What is the problem that you see here, like in inference? Because from what I would expect, if we don't mask these attention weights, we will get even like maybe very good results during training, but actually pretty bad during inference, because we will be relying on them during training, but in inference we won't be able to access them. So we wouldn't have that information.
Well, the idea is, in the way I see it, is you're trying to train the model to predict. But if you don't mask it, then now it's going into the future and knows everything. So
Exactly.
It's all building context as it builds up to predict the next word, to complete the sentence. But there is that bit that still remains unfinished. And if you don't mask it, it'll know that context too.
Yeah.
And without masking, all of a sudden you have the prediction of the words that are being generated knowing the entire corpus and so on. What good is that training? I'm sure, to Santiago's point, yeah, perhaps it gets it precisely right, but we want it to be generative. We want it to be intelligence or artificial intelligence. But if you just sort of say, here's the full picture, just tell me what's missing here. Okay, that's just a lookup. You've just spent all that computation on creating nothing but a lookup engine versus a
Exactly. Generative, exactly.
So I thought I heard a slightly different question asked, and I lost track of who asked the question, so they could jump in if I'm wrong. I thought they asked, I'm going to simplify it. Do you use causal attention during inference? And I think the answer to that is no. You only use it during training.
Yeah, exactly.
Yeah, I think it's a good point, Peter. Yeah. It's a easier way to summarize. Yeah. So this mechanism is part of building the model. Has nothing to do with inference.
Yeah, but I guess there is also something that I wasn't thinking back then, and now I think that I'm getting it. If you don't train that part of the matrix, then during inference you shouldn't use it either because you didn't train it. So it also makes sense. I mean, we are catching it because we want to create this causality, so it does not see the future. But then those numbers would be like kind of random because they have been multiplied by 0. So they are just they probably still have the initial states, that part of the triangle.
I'm not sure if I get right what you meant, Carlos.
Yeah, what I'm saying is that as it has been mentioned, we are hiding this part, the upper part of the matrix, because it's the one that contains the future tokens. And the thing is that if we hide it for training, because it's where in the part where causality kind of makes sense, then those parameters are the weights that are associated with those parameters are not going to be trained because they are multiplied by 0. So they are actually like kind of being ignored during training. So I guess it wouldn't make sense if you wanted to then activate them. It would be kind of weird. So I'm kind of understanding that we do that because of the training, but then they are those parameters are kind of useless. I mean, they are not useless. We want that triangle, but what I mean is I didn't know if that was kind of a waste or something like that. That was the question, but I guess that's the reason. As we did not train for them, then we cannot use them during inference.
Okay, let me see. Okay, so I'm also seeking out loud now. So basically, these numbers represent the degree of correlation between words, roughly speaking, within a sentence. So in this line number 2 or whatever line we take, this numbers represents the relationship between the second word to each other words. So, but the thing is that we already know all the words in the sentence when we computed these numbers with attention score or attention weight. So we knew already in advance the entire sentence, the first steps, every journey starts with the first step or whatever. So which defeats somehow the scope of the scope of the large language model, which is his job would be to predict the next word, not to know something in advance. So, which means that the entire logic of or the entire logic we took so far with these 3 attention mechanism so far basically used this let's say cheating approach where the sentence was known, the entire sentence was known to the model. And as we move forward, at least this is my understanding, this guy removes the various, let's say, assumptions from the start. He took from the start in order to make this implementation as close as possible to the natural language processing. Yeah, it's one word at a time, and you don't know what will be my next word in real life. Yeah, so this is how I see it. So now what we want here to solve is the attention of the word journey. When we want to compute the attention for the word journey in regards to or the attention of the word journey, we want to take into account only the words up to the word journey, which are the journey. Yeah, 2 words. So, and then we predict the next, or the model should predict the next token, and then based on the job of the training is to minimize the delta between the predicted next token and the real token, which we know is the journey word starts. And then when it reaches to the word starts, here, the model should look to compute. The model takes the word starts as a query, and then it computes the attention scores only up to the word starts, which means it computes the attention score only to the point starts, which is the journey starts. And then he will try to anticipate or to predict the next word in the sentence, which we know is with, and so on. So which means that in real life, in natural language processing, as we speak right now, we don't know which will be the next word. I don't know which will be your next word when you're making a sentence. You don't know what will be my next word when I'm talking. So, which means that the attention score should be somehow computed up to the present moment. And somehow within this mathematics, we need to get rid of these values and to ignore them altogether. And the first approach was to use this trill function, which basically creates, basically cancels out all the attention scores which are above the diagonal. And by multiplication of the attention weights with matrix, which is created by this function, and of course we cancel out all the values above the diagonal. So now when the model is computing the attention scores for a particular query, let's say again journey, it will take into account only the first word in the sentence, which is already known, and the current word, which is actually the query, which is journey, and will compute the attention scores for these or attention weights for these two tokens. Okay, but now because we made this stuff, now we don't have the ability. We lost the ability to interpret these numbers because now these numbers don't sum up to anything. I mean, they sum up to something, but they don't sum up to one anymore because they the previous line, the previous elements on one line sum up to one. So now by making zero of these elements above the diagonal, we have some values which are difficult to interpret, which means that we need to make sure that convert these numbers to values in a way in which we can read them as probabilities. So we need to do a kind of renormalizing of the outputs to sum up to one again. We apply again the softmax again function, and now each line sum ups to one, which means that if we would need to read, let's say, the third line, which is every journey starts, yeah, which means that for the word starts, which acts as a query, the attention the model pays on the first word is first token in the sentence is 0.38, and on the second word is journey is 0.30. So we have a kind of intuition here that at least to me this does not sound, let's say, necessarily accurate as we would read it, let's say, in real life when we make. So your journey starts. So your journey starts. So for the word starts, so the word starts, or the token starts, which is a query, the computed weight or the computed probability or computed weight for regards to the word your is 0.38, and with the word journey is 0.3. So for the word starts, somehow the word your is more important than the word journey. This is how I read it. Okay. Okay, now I need to make an additional comment with regards to softmax, and we've seen how softmax was computed in the first place before even talking about this trill function, which set all the elements above the diagonal to 0. So the softmax function, when we computed the softmax function, when we did the first normalization, we took into account all the elements in the numerator. We have all the elements, which means that somehow within the softmax function, we already have some information about the future, and which means that this mechanism to which makes 0 all the elements above the diagonal is not very efficient, because in the existing values, within the existing values, already took into account all the elements within the sentence, including the future tokens. So the solution to this new problem is to turn with, let's say, all the elements above the diagonal to minus infinite, because if it's minus infinite, here e to the power of minus infinite will be 0. So yeah. So before we, I repeat that. So before to apply this 0 or to turn to 0 all these elements above the diagonal, we used already the softmax function in the calculation of these elements, which took into account all the weights. So even if I zero out, let's say, all the future tokens, which I did, this does not mean that we get rid of the influence of the future tokens in the even though tokens are cancelled out. So when I apply this normalization, the future token already influenced the initial values. So these initial values are already somehow biased by the future tokens at the moment we applied softmax function, because softmax function, as you've seen here, contains the sum of all the elements in the emitter. Okay, so the better way is to use so-called upper triangular infinity mask, which basically, instead of putting 0, we put minus infinity for the elements above the diagonal, and all the attention weights now sum up one again. So the idea, instead of applying softmax on attention scores, we only apply this so-called upper infinity. So all the above elements in the above diagonal will be replaced with minus infinite. So now when we apply the softmax again on a row, then all the values will be 0 above the diagonal, which makes that there will be no influence of future tokens on the current calculated value by the softmax function. Any questions here or comments?
I have one question, maybe, but not related to the mask, but related to what is happening inside the softmax. Has anybody built like a intuition of why do we need to normalize also by the shape, the square root of the shape of the length of the key? Sorry, the square root of the length of the key. Does anybody like kind of figure it out?
That question, I believe, has to do with the sine, cosine similarity, distance, and so on. If it is not something that I understand very well, but that's a really good question from Santiago, if anybody knows what that is.
I think in the text it says it has to do with the numerical stability of taking gradients. And so you need numbers that are similar in scale, I think, is about all I can offer.
Yeah.
Okay. I'll take it.
What does it mean? What does it mean? It's not very, stable. What does it mean stable? Do you know,
So
Peter?
when you have, so they're talking about calculating gradients. So in general, later on, we'll be making small changes to the weights based on how much they influence the final output. And if those small changes are very small compared with the values, then of course it'll take too long to converge. You'll take, instead of training in 1,000 loops, you'll train in 10 million loops. And that's about all I can offer.
So it's a scaling mechanism, right?
Yeah, I was trying to understand why that square root of the size of the keys. I didn't get an answer in particular for why the square root or why that number in particular. But apparently the softmax, when you add a number in the quotient, when you divide the argument of the softmax, what you're doing is basically, normally that quotient is called temperature. So it's related with when you use temperature in any generative AI. With what it does is, if you have any probability of the outputs and you increase the temperature, then all of let's say that you have one value that's very likely and the other ones are very unlikely. When you make the temperature higher, basically the difference between the highest and the lowest probabilities, they get a little bit shortened. So all of them are kind of equalized. So I guess this is about getting stability, in the sense that if there is some number that is very big, we are trying to make it a little bit less, although it's still the highest probable value.
Wouldn't that still say, if it's really big, so that one entity number would be like 0.95, whereas all of the others would be like very small fractions? It'd still be that way, right? Where it's like the model just absolutely believes that the next word is going to be the word the.
Yeah, because the softmax will always answer with something, with a series of values that all add up to 1. It's a normalized function. So it's going to be the highest value is going to still be the highest, but the difference is going to be shorter.
Mm-hmm.
Makes sense.
Yeah.
Thank you.
Okay. Yeah, it makes sense. Yeah. This mechanism is used, by the way, if I can make an analogy with my field, my main field of expertise, which is networking, exactly for the same reasons, to control the scalability of numbers. Some systems use a similar mechanism, which is dividing by square root of dimensions, in order to reduce or to minimize the computational computation and to provide scalability of the system. So I think it makes a lot of sense without losing any valuable stuff.
Sorry, I had one clarification, if I may ask, Eddie, is that okay?
Yeah, please.
Yeah. So this has to do with that we kind of doing the normalization twice, when we are masking. So why are we normalizing twice? And there's this paragraph on page 76. I don't know if the book you have with you, page 76 bottom, information leakage. It talks about that, but frankly, I didn't get the intuition for why we're doing it twice. What would it seems that we should do it once? And if you're doing all this masking thing, did anyone have a better sense of that paragraph, information leakage paragraph on page 76 bottom?
For the leakage, I have the explanation, but for the double normalization, I need to think about it. So for the data leakage, the idea is that when the softmax is computed, on the first time softmax is computed for the first normalization, the attention weights already, or the result of this computation is that they are influenced by all the weights, including the future weights, and that means data leakage, that the future tokens influence the calculated value of the softmax of the, let's say, current tokens, and that makes data leakage, let's say, an issue. I mean, like by this influence of the future tokens on the let's say on the current tokens when we apply softmax. But why this
Yeah, and then later
normalization?
on we again normalize it after making that upper triangle zero.
Yeah. Let me go one step back.
So
what would
I thought the text said that numerically they end up the same. Maybe I misread that. And I think it's just an implementation detail of how they chose to present it, the double normalization. That's how I interpreted it.
Yeah, me too.
okay.
Yeah, me too, because we double normalize when doing the upper triangular matrix, the zero ones. In that case, we have to double normalize to get rid of the information leakage. But when we do the infinity triangular matrix, in that case, we're just normalizing one time, right? Or no?
No, I don't think
Yeah,
so.
actually, in the class, when he defines the causal attention class, he only normalizes once. So I guess it's probably because he's doing things step by step and probably wanted to just
Okay.
Yeah, because in page 77 and in the figure that is like 3 blocks, in that case you only apply softmax once, and we don't have to normalize twice.
Okay. Okay, makes sense. Yeah. Thanks, folks.
Let's see if we can continue maybe
Yeah.
slightly faster when we rest to see if we can achieve the goal to finish with this chapter.
Okay, so this data leakage problem is solved by using this upper triangular infinity mask approach, which now we get rid of this influence of the future tokens on the current tokens. Okay, so now we can yeah, so now when we make this multiplication, I have an error. So this was the zero out the up. With the infinite approach. Now we have again the weights, and they sum up to 1 on each row, which means that we can read them correctly as probability distributions for every query in regards to the previous tokens. So if we take, say, the fourth line, which corresponds to the token your journey starts with. No, maybe it's not the best example. Let's take the last one. So the last row, we have, let's say, the word step. And the word step, the attention the large language model should pay for this word step in regards to the word your is 119, with regards, or 90%, with regards to the word journey is 0.16 or 60%, etc. So I mean, I'm trying to see if from the linguistic point of view, or from the meaning point of view of the sentence, your journey starts with the first step, it would make sense. So what is the closest word from the meaning point of view? What is the closest word to this word step in the sentence. If we think like a human, and so according to this implementation, the closest word is starts. The closest, the model should pay
And
the
last.
most.
Starts and last. I mean, there's one more 0.1666.
Yeah, 2 times. Yeah, right. So the for this word step, the large language model should pay the biggest amounts of attention to the words starts and first. And the third one is journey. So for this large language model implementation, the word first is more important than the word journey with regards to the word step. I don't know. I wouldn't be. I don't agree with this approach, to be honest. I think the word journey is close to the word step as the word first, for example. Like it is computed here. What do you think about this human-like analysis of this mathematical representation of attention for the word step towards all the other words? What do you think? Does it make sense to you? Because for me it doesn't. For me, the word journey is close to the word step than the word first is to the word step. Or maybe I'm wrong. How do you see it? I mean, with other words, how can we be sure that the quality is performing well?
I mean, yeah, maybe it's not like it doesn't make much sense for a human yet. But what I see here is that actually most of the weights are quite even. The difference between 19 and 16 there is, but not super big. Plus, this still needs to be trained on large corpus of data, right? So
actually,
this
I did a
this
mistake.
thing is gonna change.
I did a mistake. The biggest one is maybe I need to change my I need my glasses. So the most important word is your, or the word step. Yeah, sorry, my fault. So the attention the model should pay on the word your is the biggest when it looks at the word step.
Yeah, as Michael says in the comments, these weights are still like pretty random, right? We haven't trained them.
Yeah, especially the embeddings that we have used for these are like example embeddings of only 3 dimensions, and they have random values initially. So they are not embeddings that have a meaning. So when we do the dot product, they are not gonna be like closer, or it's not gonna have semantics yet, I think.
Yeah, right now it's just gibberish. Yeah.
Okay.
We're still in the mechanics. But maybe once we get to train something, we can come back to this specific example, or maybe it's already in the book, and analyze the attention weights for that sentence. Yeah.
Have they decoded these numbers somewhere with the tokenizers that with the tokens that you are referring to?
Or I didn't get the question.
I didn't catch the question. Yeah, neither.
These tokens
yeah.
decode back to English.
Mhm.
It should be if you scroll down, Eddie.
Mhm.
I think if you decode them back, he decodes them back, right?
If I scroll down, what do you mean scroll down?
Um,
Well, I don't know how we can. I mean, this is we have a series of mathematical operations we perform so far to reach to this outcome. What do you mean to revert? Or I'm not sure if I understand correctly the question.
So these numbers, as you can refer to the matrix last row here, 0.1935, 0.1663, 0.1666. So these numbers have to be referenced to some tokens, like the tokens like step, like and other words that you were referring to. So have they been decoded somewhere? Like your journey step starts. Are you getting my query, or should I rephrase it?
No, okay. Let me see if I understand this. Okay, so let's go back to 3 steps because so let's go, for example, here where we are at go to
So
steps.
while he's scrolling, remember the weight matrices are initialized with random numbers. They're not trained yet.
Okay, so let's look there. Let me go to a couple of steps behind. Okay, so this is the attention weights matrix. Okay, we have these numbers. Can you follow me, Mayank?
Yep.
Can you hear me? Okay, okay. So let's take the second row in this matrix. So this line represents the attention of the query journey. Journey is the second token in the sentence. Yeah. We have 6 tokens, and for each token we have a line, we have a row. So this line represents the attention of the query journey. Journey is the second token in the line, in the sequence, to all the other keys, to all the other elements in the input sequence. Yeah. So the model should when the model uses the word or the token journey as a query, it must pay attention 0 to or 20% to the word your, 16% to the word journey, 16% to the word starts, 14% to the word with, 16% to the word first, and 14% to the word step. So this is how we should read this line here. And your line, the last one you asked, represents the attention of the query, step, to all the other elements in the input. So this number here on the 6th line basically encodes how much attention should the word step should pay to all the previous words in the sentence.
I believe that at this stage, if you go just a little bit at the top, that tensor that we defined at the beginning, that is just like a random
arbitrary, yeah.
Numbers. And and I believe that the thing is, if we used a pre-trained model with embeddings that actually have semantic value, then when we do this first multiplication, I believe that we would have something that is much less even than we have now, which is almost always around like pretty even values everywhere. I believe that we would start seeing with those pre-trained values something much more meaningful.
Yeah, I also now hearing you, I also have the same opinion that we need, let's say, a more realistic embedding and also training process in order to be able to read these numbers in a meaningful way. Yeah. So okay. So just to finish my answer for my answer, so basically we have these numbers, which I said what they represent here, and then these numbers, in this case, they don't change because we don't need to make any change on this line. But then we need to apply this. We need to apply this approach we discussed with softmax using minus infinity mechanism, and then we get different values for this line by applying again this mechanism. And probably these numbers can be reverted back, but I don't know how to do it. I mean, because if I answer correctly your question, if we can restore the original numbers, right? Was your question? But I'm not sure if I think I don't know. I don't know the answer. In case this was a question, I don't know the answer.
Mm-hmm. Yeah, I get clear. Thanks. Or anyways,
Yeah. So the point is that we perform different mathematical transformations on this tensor, and most likely the process should be reversible. Okay. So now the last or the second mechanism, a second mechanism which is used is called dropout, and so now in the neural networks there is a phenomenon which is called codependency, and in this phenomenon codependency, some neurons are lazy. This is the simplest way I can understand that. So some neurons are, let's say, do more work, and others are doing less work, and this phenomenon codependency means that some neurons, they observe that their neighboring neurons are very active and do a lot of work, and that's why they become lazy. And that's why we want somehow to include all the neurons to be active and to perform and to learn basically the patterns. And that's why if we drop out randomly some neurons, then also we make sure that the neurons which are lazy will start participating more and more into the weight matrix generation, and that will lead at the end to a better generalization, and also prevents overfitting, because if some of the neurons are in a sleeping mode, to say in this way, then only some neurons are very active, and that can produce or can generate overfitting. So this is the reason why randomly with a variable dropout rate, and this example is 0.5, based on the book the ChatGPT uses, or other values, other GPT models use, let's say 0.2, 0.3, but this is just for example. Some of the neurons are turned, are shut down, are switched off, basically. So the attention matrix is turned into, once we shut down the, see if I missed any step here. And also if the if we apply this approach with dropout, then the non-drop values will need to be scaled up in order to maintain the contribution to the overall attention weights. So now is my new attention matrix. And apply the dropout layer to the, and we get this new tensor here. So any questions or any other views about this dropout mechanism and the why we need to use it?
So I have a question more. So I think I understand why you need it during training. I'm unclear why you need it during inference, except that you've already used it during training, and to replicate what you've done in training, you presumably need it in inference too. Is that correct? Does anyone have any insight?
My intuition, if I allow my intuition, is that you need only during the training, because this is the moment when you want to make sure that all your neurons are active and they are learning, which means they update their weights in a fair manner. So all of them are working, to say so. And then once the weights are memorized, or no, once the weights are computed, then the inference should not need such mechanism anymore. This is my take, my intuition. But
so I haven't finished the next chapter yet, but the code snippet looked to me like it included dropout in inference. But
okay.
I didn't get past the discussion about that in the code chapter yet.
Yeah, maybe somebody else has a different or a better explanation. Or anybody which
Yeah,
does anybody know?
In this current chapter, it said that this is not done during inference. So I'm curious why it would be in the inference part of the code. But maybe we can discuss that when looking at that specific chapter in the, because yeah, dropouts are used only when training. Generally.
Okay, that makes more sense to me.
Yeah.
Yeah, for me it doesn't. I mean, well, I didn't read either the next chapter. I mean, I didn't read them with enough depth, but dropout for inference, I don't know. I see inference as as the last phase of this process when you basically benefit of the results of training. Now, whatever tricks you apply during training, these are just to optimize training, to minimize the compute, to parallelize whatever is needed to make it better, cheaper, whatever. But then when it comes to inference, then why should we apply these, let's say, tricks to inference?
Yeah.
So I think I can explain very concisely why I thought they included dropout in inference. There's a code section in the next chapter that's called forward. And so my naive interpretation is that forward is called both during inference and during training. However, I bet is a different version used for inference. Or maybe there's a flag somewhere that turns off dropout that's in line there.
Maybe
Yeah.
we should capture this question because these are very good questions, Santiago. And once we progress with these sessions, we'll address because definitely nobody, or at least I don't have the full picture. Probably most of you don't have the full picture of Sebastian's book, but enough detail level to to understand, let's say, all these interesting things like if dropout is applied or not, which phases. So maybe if we record these questions somewhere and address them later when we have a better picture of how this stuff is working.
But for the moment, what I can say is that when he implemented it in a class, he added a parameter. So he probably can change the value when he's doing training or inference just because it's a parameter.
Yeah. Okay. So now the book, Sebastian is implementing a class. So he's putting together all the code and also he wants to implement code for process to be able to process batches, which means multiple inputs, multiple sentences. And he uses the same sentence and 2 times and creates a tensor which has now 2 entries, this batch and this new dimension is a part of the sizing. So here a class basically encapsulates causal attention mechanism using all the pieces of the code we went through earlier, like the out embedding size, the initialization of the query key and value matrices, dropout mechanism is implemented, is added, masking, and then a function called forward, where he takes the new batch dimension B, number of tokens, and input of the embedding dimension, which is 3, and defines keys, queries, and values. Then computes the score using this multiplication between these 2 matrices, queries, and transpose key matrix. Then computes the scores by masking them using softmax, and then applies dropout and the target. The objective of this exercise was to compute this context vector. So what we have here, it's stacked tensor which corresponds to each entry within the batch, which had two entries. So now we slowly entering into multi-head attention mechanism, where we simply, in this case, concatenate these 2 matrices, the context vector matrices of which correspond to these 2 inputs, which in our case is identical. So the previous context, the previous attention mechanism, causal attention mechanism we just discussed about, now is considered as a head. It is considered as an entity which has the ability to pay attention to the input, to certain aspects of the input. Yeah. So input sequence has multiple, let's say, input has multiple has multiple angles. We can look at something. Yeah. We can look from the semantic point of view. We can look at something from a grammatical point of view. We call something from the creative point of view, etc. I mean, we can look at things from multiple angles. And in the previous example with causal attention mechanism, with dropout, and with softmax normalization, basically the set of these three matrices we computed for key, value, and query are now encapsulated in the concept which is called head. So it's like a head which basically contains these three fine-tuned, not yet fine-tuned, but these trained or not yet matrices which contains these weights, and then these things are now paying attention to a certain aspect of the input. Then we implement another set of matrices which should be responsible for another aspect of the input, and that will be another head of the attention. So in this way we have here, in this example, we have two head attention mechanism. In this book, which is I will share the book in a moment. What I want to say here is that the previous concept of causal attention basically is now conceptualized as a head. So as I mentioned, one set of query, key, and value matrices is one head. If we add another set of matrices, we had a different head. So the idea is to create a kind of multi-instance. Yeah, it's a multi-instance of the attention mechanism, which can run in two ways. With multi-instances of the attention mechanism, what causal attention mechanism can run either sequentially or in parallel. So the idea is that if we have multiple heads, and every head is paying attention to a certain aspect of the same input, and then we combine the outputs, we will get a very powerful representation of that input, and the model will be able to have, let's say, will be able to extract very complex patterns from an input if it's looking to that input from multiple angles. Yeah, and every angle is, as mentioned, implemented as a head, as a set of query, value, and query, key, and value matrices.
Just one comment. Sorry for the interruption. But
yeah, please.
We just reached 95 minutes, and some people are feeling like they're enjoying a lot the conversation, but they have to go. So I think we should be wrapping up in the next 5 minutes. And probably, as with all the other previous sessions, maybe we can start next one, closing this one.
Mm-hmm. And chapter 4 can start.
Yeah, I'm chapter 4, and I'll be leading chapter 4 next week.
Okay, perfect.
And just another interruption about the dropout discussion. So in PyTorch, there's a method that is called .eval. So when we train the model and the model is fully trained, we will see it later, but when the model is fully trained and we want to make inference, we call this .eval. So we set the model to inference mode, and that internally, if we are using PyTorch functions for all the model, that internally is gonna like turn off, drop out, and all other stuff that were only useful during training. I'll send a link here about the discussing that specifically. So yeah, sorry about both of the interruptions.
So basically, as I mentioned, there are two approaches. One, let's say, roughly speaking, one is sequential, and the other one is simultaneously. And in the next 3 minutes, I will cover the sequential approach, where multi-head attention wrapper class is created, which contains basically all the definitions of the functions, and is also the causal attention mechanism implemented earlier with all the dropouts and things we discussed about. And then here we have a sequential approach for the heads. The context length is using the same size for the input 32 for the output, and an instance of this class. And the idea or the end result is that we have these tensors. We have a tensor which is concatenated from for both heads. So we have a sequential multi-head attention mechanism implemented in this example with these two instances of self-attention, and basically these are the weights corresponding to each instance of the weights for.
So, how are the heads related to the embedding dimensions? Do they share that too?
How the heads are related to embeddings? With the question?
Yeah. Mm-hmm.
Okay, so these are related to the embedding in the way in which we computing the attention weights. Okay, we computed the attention weights by multiplying the query and key matrices, yeah, and query and the key matrices the query and the key matrices should take into account the these two dimensions for the input and output for the embeddings. In order, so it's about algebra here. I'm trying to figure out a better answer. Give me a second. We have a better explanation. If somebody has a better answer than I know my answer was not very clear, but come on. My internet is pretty slow.
Yeah, for me as well, the
Okay.
head intuition, I mean, given that we have done already the whole embeddings, context vector, query, key value, trainable weights, doing a head on top of that intuition was not clear. I mean, it does say in terms of, let's say, different relationships, but I guess that's something we can pick up from next week. Yeah, this head part, a little bit more analytical perspective would be helpful.
So here we have a tensor which has 6 rows, yeah, which corresponds to each token, and 3 columns, which represents to the 3-dimension use for embeddings. This is how we agreed from the beginning that the embeddings is 3-dimensional, yeah. It's clear so far? So it's a 3 times 6 matrix. Because 3 is the number of embedding vector you use for each token. Then we need to compute the attention scores according to this picture here. And okay, go to the. I need to go to the trainable matrices. Okay, so we said that in this trainable matrices approach, yeah, we introduce these 3 training weight matrices, yeah, and we use them to translate or project the input embeddings into query key and value vectors. And in order to do that, each matrix should have should have a certain shape in order to get to this result. Yeah, but I think we can. I will cover this calculus next Sunday. I didn't have time. I planned for today to have some hands-on matrix multiplication. I didn't have time, but for the next call on Sunday, I will make it because I think it's useful to have a mathematical view on the computation end-to-end. And then the code implementation will be relatively easy to run from GitHub. I will do that. I will do that for next Sunday because yeah.
Good. Thanks a lot, Eddie. My intuition about heads is also not fully formed yet, but so far, my best analogy so far is like, I don't know if you're familiar with ensemble learning. Like, let's say we train multiple models and then we kind of ensemble them in a single one. That's as far as I can get with heads. Like, we know the attention mechanism works, but now we're trying to do it many times for as many heads we have. And at the end, we're gonna end up with different context matrices, and then we combine them. And basically, hopefully, that works better than just doing it once. That's my idea about heads.
Yeah, but the question was related to embeddings dimension, and
Yeah,
it has
yeah.
to do with matrix
Yeah.
multiplication. How, in order to multiply 2 matrices, there are some prerequisites.
Yeah, I just got lost a bit in the current conversation now, and I was chatting with someone about heads in the chat, and then I just jumped in with the heads. But
Yeah. Okay, so for the next Sunday, I will finalize this chapter 3. I will make a whiteboard. I'll make a whiteboard with all the mathematical. I have it on paper, all the mathematical calculations. I need to put it on a whiteboard. I didn't have time, unfortunately, this weekend. And then it will be a little bit easier to follow.
So next week we will do chapter 3 and chapter 4 combined, or?
Well, from chapter 3, there are only one mechanism from multi-head attention, which probably will take me, I don't know, 10, 20 minutes. And probably, I will need also to go through again the at least 1-2 steps behind to make sense about multi-head mechanism. So I would estimate 30 minutes. And then Santiago will start with chapter 4.
Good.
For the next hour, right, Santiago?
yeah. If you can make the first part 20 minutes, I would say would be ideal. I don't know if that's too much to ask. So we can get very far over chapter 4.
Yeah, I think attention mechanism is one of the most difficult and complex aspects of a large language model. That's why, even though 3 weeks might be, let's say, a long
Yeah.
time, but I think it's an important part, and
Yeah.
it contains a lot of knowledge, and it's complex. And
Yeah.
while I received the
True, true,
questions,
true.
I realized that also for me some things are not 100% clear. So that's why I think if we spend another 30 minutes,
Mhm.
maybe will be better for everybody.
Yeah, indeed. Okay. All right.
Cool. Thanks,
Yeah,
Eddie.
but again, we are here. Yeah, welcome. I want maybe you, Santiago, can emphasize my point is that we all try to learn and to understand this stuff, and at one moment each of us has, let's say, this small contribution to make a presentation, but does not mean that they are necessarily experts and state-of-the-art experts, and they know inside out everything. So it's a process.
Mhm.
It's a process, and everybody, all the guys in this call, should be aware of that. And just because somebody is doing a presentation does not mean that he's a super master of that.
Mhm. Yeah. It's a fun experiment, like to teach something that you are currently learning. So,
It's a multi-head
The
transformer.
multi-head attention mechanism, yeah, exactly.
yeah.
Multi-head attention mechanism, yeah.
Best way to learn is to teach it. I mean, number one, go to a good school and study it. Number two, better way to learn is to write a book about it, as Sebastian's done. But if you want to be a true master, teach it.
That's right.
Yeah.
It's interesting that, when I did this stuff on paper, I mean, I computed all this stuff on paper, but, even though some things were clear in my head, while I'm receiving the questions, I realized, oh, hold on, so some things are not so.
Mhm.
So
Yeah, that happens.
yeah, but I'll make the whiteboard. I'll make the whiteboard, and I'll make the mathematical calculations of this stuff, and at least some questions will be answered.
So
Hopefully.
there's a lot on this. Just reiterating what Eddie just said, there's a lot on attention mechanism, this multi-headed layer, and it's just so the authors of the article of the main 2017 paper calling it "Attention is all you need." They kind of, tongue in cheek, it was very memeable title, but there
Yeah.
was much more to it, whether they realized it or not, that helped outline, sort of being the basis for that whole transformer architecture. The transformer architecture, which we're going to build in the next chapter. Thank you, Santiago, for taking the lead on it. And that has proven to be so versatile. No one's been able to evolve on it. You can improve it, you can tweak certain things, and that's why it's so powerful, because it has so many capabilities, all the layers, and so that you can refine it in a really cool way. But that the core architecture, which Eddie and Santiago are helping us cover by next week, that is foundational. It's what you can apply instead of we're doing text data, but you could apply that towards video, images, et cetera, et cetera. I mean, there was a news in the last 12 hours that OpenAI's Sora model, the text to video generation, it was leaked out by some people who were given early access to it on Hugging Face. As soon as, of course, OpenAI found out, they locked it out, but it was opened up for anybody using Hugging Face could just pull that API and start generating it. And it's already created a lot of ruckus. And where I am in Miami, we just are starting Art Basel with all of these artists and digital art and so on. This is scaring human artists because these models, this transformer-based model that creates, we're just creating text, but generating movable images and movies. And this stuff is pretty awesome.
And scary at the same time.
Yeah, and again, the transformer architecture, not just for images, but you can apply this same, just as we did machine learning models and ensemble models, as Santiago mentioned, apply this transformer architecture with any kind of data, particular data. One of the things I've worked on was time series for sensor telemetry and equipment. So if you were trying predicting when certain equipment would fail, like a windmill or so on, but rather than using a machine learning model, use a transformer model. Yes, and yes, that was where Karpathy has that brilliant take on it, where he's the one who says, "Yeah, it was so memeable."
Yeah. And also, yeah, I mean, his articulation of it is almost like a general purpose computer that, I mean, it has stood the test of time, that people are doing tweaks on it.
Yeah.
But I mean, it still has a lot of, power to it. But it's also interesting, I think he or someone else says that a couple of 2-3 more transformer style innovations are required before we reach AGI or something. But anyway, that's beyond my pay grade.
Well, at the end of the day, it's still this same transformer architecture, right? It's still that. You're just refining it.
Yeah.
And it just lends itself really well to the hardware that we had available, GPUs, because it's parallelizable.
Yeah. And I loved, I think, Dario or Ilya's take on it. These models just want to learn, I mean, so the setup has been that, with the transformer, that the more you give them data, they're just hungry to learn, so that they can. So rather than figuring out how to make them think like humans, you give them compute and the hardware and just throw information at it. I think Sutton's he had this bitter lesson. It's a brilliant blog post for me. It has been recently when I read it, that rather than putting in a lot of human style thinking models, set it up for it to learn and to just devour and everything and figure out underlying patterns and representations. Yeah, but yeah, it's just me beginning to think.
Naveen, you make a really good point with that. But however, let's not anthropomorphize the model. The model isn't learning. It's us humans applying that architecture model and throwing all that data and getting it to do all this and letting it and creating maybe that self-perpetuating mechanism. It's not the model taking on a life of its own. It's because we humans,
True.
myself included, want to give that mechanism life.
Yeah, which is what we are doing, more and more. But in the early days, I think it was more like, like the games of chess, and can we feed in, how the best chess players are thinking, and then recreate that. But and that seemed the most, apparently the most intuitive and popular way to do it. But that didn't run on as much as, throw in a lot of data, let it figure out strategies on its own there, and then do that. Yeah, so that's what I meant. We should never anthropomorphize machines and silicon and chips. Yeah,
indeed, we are not anywhere near AGI, but that's just my biased view.
Yeah. Great, thanks, Eddie. Thanks for patiently making us think about these final details.
Yeah,
incredible patience on your part to work through all the details.
And all the questions, Carlos, Santiago, I think Peter, thank you all.
Yeah.
Great questions and just awesome engagement.
Yeah.
Thank you all, and thank you, Eddie, for the presentation today.
Welcome.
Cheers, everybody. See you all next week.
Okay. See you next week.
Bye.
Ciao.
Bye.